So the instrument that our group had assigned was X-ray crystallography, and the members of our group are David Russell, Wesley Lamberson, Claudia Nardone, and myself, Abigail Anderson. So the 4 parts that we'll be going through are general information, the functions of X-ray crystallography, performance information, and real-life applications of this instrument. So first, I'll be presenting general information about this instrument. So why is X-ray crystallography used? This is a technique that reveals the structure of matter at the atomic level, and in order to do this, scientists need to obtain a crystal to expose to X-rays, and then use a pattern of X-rays as they pass through the crystal to calculate the molecular structure. The crystals scientists produce need to have certain characteristics to ensure high-quality results. There are 3 main categories of samples that are used in X-ray crystallography. First are fibrous materials that have crystalline structures. These materials demonstrate the layer line concept of crystallography, and any bent layer lines mean the pattern needs to be straightened. Next are crystallites. For this sample type, there needs to be tenths of a gram of material, which is ground into a powder. A homogeneous and single-phase material is best for identification, but for mixed materials, the detection limit is around 2% of the sample. And finally, there are crystals. These are the hardest type of sample to produce with the best possible quality because of the many traits that make up a good quality crystal. So here are the main attributes that are considered when producing a crystal for X-ray crystallography. The first thing to consider are flaws or defects that can be viewed under a microscope. If the crystal seems to be cloudy, have cracks, ingrown crystals inside, or growing out the side, then it should be discarded. Additionally, if there are multiple crystals stuck together or thin plate-like crystals stacked on top of each other, then they should not be used. Next, the overall crystal structure should be transparent and have polarizing capabilities. Additionally, crystals with a powdery surface should usually be rejected, but if the crystal is still translucent, it can be used if there are no better substitutes. Thirdly, the crystal should have regular, smooth faces, and any crystal with jagged or lumpy edges usually means that there are several crystals that are joined together, so that sample should be rejected. In the ideal situation, the best crystal shape should be a sphere because it can minimize absorption effects. However, the next best options are either a cube or a prismatic crystal that has each type of dimension about equal to each other. A good rule of thumb is to produce the biggest possible crystal within the limitations of the X-ray beam being able to totally surround the crystal. If it is in the form of plates or needles, then the thickness can be at a minimum of 0.03 nanometers. Finally, a good quality crystal should become uniformly dark every 90-degree rotation under a polarizing microscope, as the polarized light is extinguished. This is done because misaligned fragments will not darken at the same angles as the main part of the crystal. So, crystals where there is no dark region, the dark regions travel, or there are streaks of colors or blotches of darkness should be used with wariness. So now I'll have Claudia Nardone present some functions of X-ray crystallography.
So I'm going to talk about the basic functions of X-ray crystallography. There are a few types of measurements you can make: single crystal crystallography, powder diffraction, fiber diffraction, grazing incidence diffraction, and X-ray reflectivity, and lastly, small angle X-ray scattering. For single crystal crystallography, you will need a single crystal, and it is placed in different orientations in the X-ray beam. This results in diffraction patterns shown in the picture. The positions of the spots give information about crystal lattice symmetry and dimensions, while their intensities can be used to determine atomic positions within each unit cell. A unit cell is the smallest group of atoms that are repeated to create the crystal lattice. The shape and widths of each individual peaks can be analyzed to determine details of the crystallite sizes, as well as microscopic strains and defects. This technique generally yields more information than the other techniques. However, it is also the most difficult. Measurements have to be made at many different orientations in order to obtain the necessary information. A very important application of this technique is protein crystallography, a central technique in molecular biology. This technique requires high-quality crystals, which is often a very hard task. Next is powder diffraction. In contrast to single crystal crystallography, powder diffraction uses a sample consisting of a mixture of many crystallites, often in the form of a finely ground powder, hence powder diffraction. Powder diffraction yields patterns of concentric rings rather than sharp defined spots as shown in the picture. These rings each have the same scattering angle 2 theta that a single spot would have had in a single crystal pattern. It's much easier to produce a powder sample rather than a single crystal, and with this technique, crystal structures can still be solved as long as they are relatively small and there isn't excessive overlap between peaks. A method called the Rietveld refinement is often used to determine crystal structures that is most likely to have given rise to the observed pattern. Just like with single crystal crystallography, the shapes and widths of the individual peaks can be analyzed to determine the details of crystallite sizes along with microscopic strains and defects. This technique is most often used in mineralogy for phase identification. A sample of mineral or clay often consists of a mixture of different crystal phases. The fingerprint of a powder diffraction pattern can be compared to a database, and that's how they determine which phase or phases are present. Next, fiber diffraction. The fiber diffraction method is an intermediate between the single crystal and powder diffraction methods. The sample needle is usually an extruded fiber with a well-defined crystal axis aligned along the fiber axis, which is also known as the meridian, and cylindrical averaging about that axis. A famous example of this technique was the 1953 determination of the structure of DNA. In the case of DNA, growing true single crystals proved to be challenging, but the additional orientation of the diffraction pattern due to the fiber geometry was enough to deduce the helical form of the DNA molecule. This method is often used when studying long-chain molecules such as DNA or columnar structures such as discotic liquid crystals. Next, grazing incidence diffraction, GID, and X-ray reflectivity, XR. Grazing incidence diffraction and X-ray reflectivity are closely related techniques. They utilize the fact that when a beam of X-rays impinges on a surface at a very low incident angle, the reflectivity is greatly enhanced and the beam penetrates only a short distance into the surface, as shown in the picture. In a typical GID measurement, the incident angle is fixed and the intensity is measured as a function of the scattering angle 2 theta. The resulting intensity profile can be used to establish the 2D crystal structure within the plane of the film. In a typical XR measurement, the scattering angle is fixed at 0, and the reflected intensity is measured as a function of the incident angle. The resulting intensity profile can be used to determine the thickness of the layer and in some cases, reveal information about the electron density profile within each layer. Lastly, it's small angle X-ray scattering, SAS. SAS refers to experiments where the scattering angle 2 theta is small, which is less than 10 degrees. From Bragg's law, this implies that the length scale of the objects being probed is fairly large, from 3 to 100 nanometers. SAS has been used to study self-assembled systems such as block copolymers that have periodic order with repeat distances much larger than a single molecule. And the image shown here is a small angle powder diffraction pattern. Onto instrument components. Although there are many possible permutations, X-ray crystallography instruments incorporate these main components. First, a means of producing X-ray radiation, a type of collimation, and a detector to detect the scattering. Now I'll pass it on to David Russell, who will talk about performance information.
All right, good evening, everybody. As Claudia just mentioned, my name is David Russell, and I'll be going through the performance information of the X-ray crystallography machine. First and foremost, there are 4 main categories of instrument performance. These are accuracy, precision, resolution, and then sensitivity. I'll be going through each of these one by one. So first and foremost, we have accuracy, which a simple definition of such is being correct and or precise. So when setting up the experiment, there are many factors that are involved, such as it must be a clear crystal, the crystal must not be cracked, and the crystal must be centered within roughly 25 nanometers of the X-ray beam. So then when getting results, accuracy will be dependent on these initial factors, such as quality of crystal, strength of X-ray beam, etc. Thus, to ensure accuracy, the scientist will perform multiple experiments to ensure that the experiments are indeed valid and accurate and negate the negative effects of all these multiple variables. Next will be precision, which is being exact and or refined in measurement. Now, the X-ray crystallography machine is extremely precise. Its precision is measured by angstrom units, which is 1.0 times 10 to the negative 10 meters, or 1/10 billionth of a meter. This precision actually allows the X-ray crystallography machine to even measure the length of atoms and the bonds between them. For resolution, it is the observable distance between two distinct objects, or the shortest distance between separate crystal lattice planes. It's on a spectrum. That's how they measure resolution, either by 4 angstrom, which would be considered poor resolution, going to 1.5 angstrom, which would be considered good resolution. The median resolution for this X-ray crystallography machine is actually 2.05 angstrom. And as mentioned earlier, angstrom is 1/10 billionth of a meter. For further reference, the length of a bond between two carbons is actually 1.5 angstrom. And then lastly, it's sensitivity. The definition of sensitivity is the smallest numerical amount of change that can be detected. So in simple terms, if machine A can detect changes between the 100th decimal, then machine B can detect changes between the 1000th decimal, then machine B will have a higher rate of sensitivity. This actually carries over to the X-ray crystallography, because X-rays have a wavelength between 0.02 angstrom and 100 angstrom. As such, the crystallography machine can only detect values within this ratio. But again, as mentioned earlier in the resolution section, it will normally reside within the 5 angstrom to the 1 angstrom range. In terms of actual sensitivity, it's between 0.01 angstrom and 0.02 angstrom, or it's sensitive up to the 100th decimal of an angstrom. And now for the real world applications, I'll hand it off to my partner, Wesley.
I'm Wesley Lamberson, and I'll be doing the real world applications of X-ray crystallography. So X-ray crystallography has been used since the 1500s, but has been more recently increased in productivity in the late 1900s. It's also known as X-ray diffraction, or can be abbreviated as XRC. It's widely used in the determination of crystalline structures, and it has a long and complex history with biology and the function of the different structures of the crystalline elements. So James Watson and Francis Crick is the first real-world example of X-ray crystallography in use. It was done in the biological field when they proposed the structure of DNA, which they proposed as a double helix, and they did so using the work of Rosalind Franklin and Maurice Wilkins. So they use this discovery was done in 1953 when they proposed that it was a double helix, but they used the X-ray crystallography machine to show the bond links between it and to determine its shape. That top picture is an example is a picture from the experiment itself, and the bottom picture is a picture of the first drawn template for it that was given in the primary source. The importance of this discovery was that it led for a more intricate study within the field of biology, and it opened the door for inquiries into the human and animal biological systems at the microscopic level. The next real-world example was much more recent. It was a confirmation of a 1-electron sigma bond between 2 borons, so covalent bond. This study was done in 2014, which confirmed the existence of this bond after it was proposed by Pauling in 1931. It was done on the basics of theoretical chemistry. It proposed the existence of an H2 plus radical cation, which detailed the physical nature of the chemical bonding. One of the reasons it took so long for it to be confirmed was because single electron bonds are very elusive because they have a very high reactivity, meaning that they're only there for a split second before they disappear. So the existence of this bond was proven not only through the use of X-ray crystallography, but also through a matrix isolation, because X-ray crystallography was unable to capture it at the moment by itself. The importance of this is it provides a different model for the sharing of an electron between covalently bound compounds, which allows us for the understanding of absorption bands in the visible light spectrum. And this model on the right is a non-planar view, and it would be found in the natural localized molecular orbit, meaning that it would have a free shell, meaning that it wouldn't fall into the valence electron shell category.
And then these are our sources. Do we have any questions? Awesome. Well, thank you all so much for listening to our presentation.